Okay, so often what I kind of do is a bit like magic. Last weekend we were in London and we watched the Harry Potter thing, so I can't actually give you the kind of magic shows, and I'm not going to go up on wires and fly around the auditorium, but this is a bit, cryptography is a bit like a magic show. We do stuff that you just think it should be impossible, and even cryptographers think about what I do is kind of a bit impossible, but I'll give you a bit of overview. It's already been said, but the reason I want to do this slide was to kind of show, I did maths. Yeah, this is like everyone goes on, falls asleep at that point. And then I kind of started doing more applied stuff, and then I realized there's more money in crypto, basically. So you start moving to Hewlett-Packard, and then my kind of goal in life has been to bring maths into the real world. So like heavy maths that everyone thinks is kind of pointless, to bring it into the real world. So there's a famous quote, G.H. Hardy. He wrote a book called A Mathematician's Apology in about the 1940, and he said there are two really, really good things in science, because everything else in science had been tainted, because it'd been tainted to use for bad ends, it'd been tainted to use for war efforts or for useful things. And he claimed that there were two really, really good things in science that had no application whatsoever. One of which was relativity. Okay, so this was 1940, so this was very pure and theoretical, and relativity obviously has applications. And the other thing was number theory. Okay, so whilst it might have taken the Manhattan Project to turn relativity into an application, useful or not, depends on your point of view, it took much more longer for us to find applications of number theory. So, but since the 1970s, our entire society has essentially been based on something that Hardy thought was totally and utterly useless. So there we go. So I've done all sorts of things and blah, blah, blah. And currently I'm in Leuven. So now if you think this is kind of takes an exponential distribution, so the time length gets longer and longer each time, then obviously I'm going to be in Leuven until I die. Alternatively, it could be a normal distribution. You never know. Anyway, depends on which is your favourite distribution. Okay, so I've done some papers and stuff. I'm trying to get to 100. So come on, students, let's get to 100. Let's open those bottles of champagne when we get to 100. And I like doing stuff in the real world. So in the past, I have founded a company with Frederick Vercauteren, who is also a member of staff at ESAT, and at the time was in Bristol, and we set up a company called Identum. It wasn't called Identum at the time because academics are really bad at coming up with names for companies. So we called it something like Argylcom, because Argyll was Welsh for secret, and we were close to Wales, and we thought no one would understand that title, but no one would also buy a company called Argylcom. So it was renamed to Identum. This was sold to Trend Micro in 2008. And then in 2013, we founded, with Yehuda Lindell from Bar Ilan University in Israel, founded a company called, again, academics are shit at coming up with titles for company, we called it Dyadic Security. Also, no one's going to buy a company called Dyadic Security, so the marketing people come down and goes, Unbound, because Unbound sounds good. You can put Unbound in your deep, movie trailer voice, Unbound, and you kind of feel like, yeah, I'm gonna go buy that company. Yeah, so that's so if you've got a few million, well, quite a lot million, please buy us. So we've got a number of Fortune 500 customers and investments by Goldman Sachs, Citi Ventures, and Innovation Endeavours. If you don't know who Innovation Endeavours are, that's Eric Schmidt. If you don't know who Eric Schmidt is, really get a life in IT, please. Okay, he's the chairman of Alphabet, okay, which, if you don't know what Alphabet is, get a life in IT. They own Google, right, okay. But my favourite baby, academic baby, obviously, is the Real World Crypto Conference, which I founded with Kenny Patterson in the year of we started it as part of the Turing 100th birthday celebrations in 2012. And this has grown to be the biggest conference in cryptography in the world in the last 7 years. Now has 700 people turn up to it, and it's the place where the real world meets academia. So instead of keeping like academia and industry apart, we bring them together in a sort of a lovely environment every year in January, just to cheer you up after Christmas. We give you some crypto, and that's really that's my favourite baby of everything. That's my favourite thing. Anyway, so what do I do? Well, okay, so when I explain what I do, if you've seen me talk before, you know exactly what's coming here, and I apologise for all the same jokes. Okay, so what happens is that when we started, so there's this area called multi-party computation, which was a very theoretical thing, and we decided we're going to turn it into something practical. And then the first thing you think about, if you're an English person, is how do I make money? And then the answer you get is you go to the banks in London, because that's where all the money is. So you turn up to the banks and you go to the top of these big skyscrapers in London. And unlike when you phone, like if you phone like a tech company, if you phone like a Google or a Microsoft or whatever, and you phone them up and say, I've got a really, really cool piece of tech, they go, yeah, right. And they don't listen to you, and they kind of like ignore you. And yeah, if you phone up a big trading company, you get invited to the board meeting, and they're really clever, unlike the people who work, because that's where all the money is. So the clever people go work, well, in England anyway, the clever people go work for banks and the big financial institutions. I'm not like the Barclays and whatever. These are like the ones that do the trading, the rich ones, the ones with the Ferraris. That's where you go, right? So there you are, and you're giving the presentation to the board, and you've got to think, how am I going to appeal to them and motivate what I'm doing? So here we go. They're bankers, and they're going to go for lunch, right? And they've got a problem, is who's going to pay for lunch? Now, they've all got bonuses, that's how they bought their Ferraris, and it is completely the most fairest thing possible is that the richest one pays for lunch. The one who's got the biggest bonus should pay for lunch. At which point, the room goes dead. Oh my God, we have this problem every day. How, oh my God, he's going to solve the one problem that bankers are really interested in, is working out who's been given the biggest bonus, okay? And you can kind of see them, they're all kind of like, oh, this is going to be interesting. Okay, so we're going to see this problem. Who has got the most money? Who's got the biggest bonus? So this is what we're trying to solve with multi-party computation. We have multiple parties, there's 4 of them here, and they want to compute something. Who has got the biggest bonus? Okay, so if you're a mathematician, you're computing the argmax function. Okay, so that's what you're trying to do. This is a function with inputs, and you want to output the index I, which maximizes the values xi inputted by player I, okay? This is actually an old problem. It's called the Millionaires problem in the 2-party setting. It was introduced by Andy Yao in the 1980s, for which he won a Turing Award. Again, since before, if you want to win a Turing Award, you have to, that's the Nobel Prize of Computer Science. If you want to win a Turing Award, you're more likely to win a Turing Award if you do cryptography, and you're far more likely to win a Turing Award if you do multi-party computation than any other area of cryptography. So it's the way you kind of play the probabilities to get your probability of getting the Turing Award. Now, if you win a Turing Award, you win $1 million because Google are now sponsoring it. But when Andy won it, it was just like he just got the award. Okay. Anyway, so we want to compute this function. Now, if we were religiously inclined, we would go, there's a God. All we have to do is everybody just has to kind of close their eyes and pray and say, I've been given $1,000 bonus, and the other one's going, I've been given $1 million bonus, and I've been given a $10,000 million bonus or whatever. And then the God would actually say who should pay for lunch. But we're cryptographers and we're atheists. Okay, so God doesn't exist. So what we have to do is we have to replace God with a protocol. And so what we do is we create a cryptographic protocol, which is basically a bunch of computers talking to each other. And what we want to do is, by talking, we want to work out who has got the largest amount of money. And that is it. Okay, at this point, all the bankers go, he can solve our problem for us. That's good. Okay, so we'll come back to the bankers in a minute, but let's leave it at that. So this is what we're trying to do. Everyone gets what we're trying to do is compute a function without revealing anything about the inputs. The only thing that would be input, so suppose Mr. Moneybags here from Monopoly has been given the biggest bonus. He learns that he's the richest. He is at one point happy and also on the other point sad because he has to pay for lunch. This person, whoever this is, these 3, wherever they're from, they learn that Mr. Moneybags has got the largest bonus, and so they're also a bit unhappy because they know they haven't got the largest bonus, but they're also a bit unhappy because they haven't got the largest bonus, but they're a bit happy because they don't have to pay for lunch. But this guy has no notion of whether this person has got more money than him or not. So the only thing you learn is the output of the computation. You learn, everybody, all they learn is that Mr. Moneybags earns the most, not what. Okay? Okay, so let's put this in context with other parts of cryptography. So cryptography is a triangle these days. So what we usually do, traditionally in cryptography, we look at data and transport. So if you look at stories from the Second World War, if you look at the German Enigma machine, or the Lorentz cipher, or the British Type X, what we are trying to do is secure data and transport. And this is what you do when you connect to something on the internet. When you connect to Amazon or other shops on the internet, you encrypt all your data, your credit card details, and you securely transport it to the other side, because the person in the middle is trying to get your credit card details or whatever. So we secure data and transport. That's what cryptography traditionally did. So if you look at historical cryptography, this is what it did. And then people started losing laptops on trains and all sorts of other things, or they started carrying data around in their pocket on a mobile phone. And then we started to have to secure data at rest. So here, what you would now have is you now have on all of your laptops or on your mobile phone, you have hard disk encryption on your phone. You might not use the hard disk encryption, but you probably should. You would have database encryption. When you store data in a database, you'd store it in an encrypted form. If you want to store keys that are used for cryptography, use special devices called hardware security modules, HSMs. We'll come back to those in a minute. And this is where you store data at rest. Now, there's something about data that's really important, is that you use it. Actually storing and transmitting data is completely pointless unless you actually want to use the damn stuff. Yeah, that's the reason why you store it and transmit it in the first place, is because you want to use it. So cryptography, and generally security in general, has never, except for the last 10 years, worried about actually how do we secure data whilst we're actually computing on it. So that's actually what we're trying to do, is we're trying to, this is old stuff, you know, this is old stuff. This is what Vincent did, yeah, this is old stuff. This is AS, yeah, so this is kind of the old cryptography. What we want to do is move it to new cryptography, which is actually how do we secure the data whilst we're computing on it. So this is the holy grail of cryptography. And why is it a holy grail? Because it enables so much applications. So for example, you can think of voting as a secure computation. What I do is I vote, which what I do is I decide whether I'm going to vote for Trump or the other one, or I vote for X or Y or whatever, and then I encrypt, and then the electronic voting system would encrypt my vote, and then what I want to do is work out from the encryptions of the votes who's won the election. And I want to do this in a way that doesn't reveal, one, how each individual voted, but two, also is guaranteed that the correct result is produced, yeah, that you can't influence the outcome of the election just by twiddling with the software in some way. So that's voting. GDPR is a big driver. So if you haven't heard of GDPR, also get a life in tech. So GDPR is this big thing, big regulation to secure people's privacy. Securing people's privacy is about securing the data on which they communicate or they process. Yeah. So if we want to protect people's privacy, well, actually what we need to do is compute on the data whilst it's in encrypted form. Genomics, you might want two hospitals to combine genome data in a drug trial, but you don't want to do that without revealing. You want to do that in a way which doesn't reveal the identities or the genomes of the people that you're actually processing. And we'll see issues to do with public policy later. So going back to our bankers, you can't do a talk on MPC without talking about Sugarbeet, right? So every talk has to contain the word Sugarbeet in it, because in the mid-2000s, the Danish, there's a university in Denmark called Aarhus, which has now formed a company called Partisia, ran the first computation done in a real application using MPCs. This is only about 10 years old, this technology in the real world. So what it did was it basically, in Denmark, they had a monopoly, they have a monopoly supplier of sugar, a monopoly buyer, and what they really want to do is work out what the market clearing price is. And they would do this with pen and paper in the old days, and this would take about 2 weeks of pieces of paper going backwards and forwards. But then they could run a computation which computed the market clearing price, which is basically, you just want to compute, if you economics 101, want to compute where the two, the supply and demand curve cross. So this is an old example. Now if we go back to what I was talking about with talking to traders in London, there's something called a dark market. A dark market is actually where most of the stocks are traded. Most stocks are not traded on the open market, on the Dow or the NASDAQ. What they've done is they're traded on dark markets, because if you're a big pension fund or a big other mutual fund, you might want to sell $100 million worth of Microsoft stock. And the fact you say, I want to sell $100 million of Microsoft stock, makes the price plummet. So when you want to rebalance your books, what you do is you rebalance them on dark markets. So there are dark markets which are about 40% of stock market trades. They're not on the high frequency trading, they're not you or me trading, but these are the big, heavy users of stocks. And so these are done on dark markets. Now when we talked to the dark market operators a few years ago, they went, we don't need MPC because the regulator requires us to be a trusted party to run the market. And therefore, there's no need to do it in a secure manner. Turns out, if you have a bunch of financiers and you give them the opportunity to commit fraud, then they will commit fraud. So in the last 2 years, dark market operators are now being treated by regulators as actually a hostile player, because they've been running front-running operations to manipulate stock prices and make large amounts of money. So now we've been looking with some people in the UK, and we're talking to Financial Conduct Authority in the UK, is looking at how we can do dark markets, to take the Sugarbeet example and then apply it to stocks and shares that are run on dark markets. So we've been looking at this with one of the PhD students here in Leuven, and we've done some examples, and we'll kind of how do you actually run the dark market mechanisms, what's the best market clearing mechanism, etc. And we've done some work on this, and it's going to appear in Asia CCS later in the summer. And so we've been using this system called Scale Mamba, which is this cool thing from Leuven. It's the story about the reason for the title I won't go into. But we've been looking at different ways of running it. So continuous double auction, this is how usual stock trading is done. But volume matching is what's actually done in a number of dark market pools. And we can actually process about 2,000 orders a second, or 1,000 depending on the type of how many parties there are within the system. And this is actually quite efficient because, again, we're not doing high frequency trading here. These are for the big stock market players that are the big pension funds rebalancing at the end of the month, say. Okay, so here we've got some really cool numbers which allow us to see that this is now practical in the real world. So I'm going out to the Financial Conduct Authority to actually have a look, explain this in London in August sometime. Okay, so that's one example. Another example we're working on, again with this Scale Mamba system we've developed in Leuven, and also with a company called Galwar in the US, is a DARPA-funded set of projects to actually create a database which we've called Jana, which I can't remember why it's called Jana, but it's called Jana. And what this does is this allows you to have an encrypted database, and then you process the encrypted database using our secure computation system that we developed here. And this is a number of US government style applications have been created. I'll talk about a few of them coming up, which is public policy. The UN and various national censuses have been interested in this work, so there's been a UN report on this in their global data gateway thingy that they did a few months ago. And Senator Wyden, who is the senator for Portland, Oregon, therefore on the west coast and therefore cool and dudish, unlike the ones on the east or the middle. Middle's the worst, yeah. So he's actually got MPC. So this technology, multi-party computation, actually mentioned in US legal in the US law. So there's acts of Congress which mention multi-party computation. This is kind of like the coolest thing ever, because 10 years ago this was completely theoretical. Okay, so the idea is to create what's called a knowledge-based policy in the US, because apparently some people in the US actually want policy to be based on data and reality rather than just making it up on the hoof. Surprising though that may seem, yes. Okay, so an example here is evidence-based decision on policy. So for example, you might have the US Census, the IRS, their version of the tax authority, and some, what's that? Oh, I can't see that from here. Something, federal something. And basically they want to combine their data, but actually the Census Bureau does not want to give too much information to the IRS because that might breach some confidentiality that was in the Census Act. Ditto, the IRS doesn't want to tell just the idiots in the Census Bureau everything about everybody's tax returns. So what you can do is that they can actually take their data, we encrypt it, put it in this secure database called Gartner, and then the public policy researcher can now query the database with queries about people, queries, statistical queries, that they would, so they can create better public policy. And because Gartner also includes differential privacy on top, we can actually ensure that individual people, their privacy is not broken or not threatened by this ability to merge databases together. So this is there's been a demo of this created, and it's been one of the focuses of the evidence-based policy initiative in the US. Another example is actually an act of Congress called Know Before You Go, because in the US each act has to have some trendy title. So here the idea is that someone wants to go to university and they want to know, is it worthwhile going to university given how much time it's going to take, what the graduate loans are going to be, what benefits they're going to get, are they going to be able to repay their loan, are they going to get a good job, etc., etc. So here you take data from the census, like what's their statistical information about their ethnicity, where they come from, where they live, etc., what the education is like in their area, IRS, whether people who've gone to this university and done this thing have earned a lot of money, because the evidence of whether you've earned a lot of money is in your tax return. What loans you've taken out, so we've got databases on this. We've got institutions, so Harvard, Yale, Stanford, they don't want to tell the IRS, they're Americans, they don't trust the government, right? So these people, these universities do not trust giving their information to the government. So they want to keep, how long the person was at university, did they pass, did they fail, what were the scores on the various courses, etc. And maybe they've also come out of the services and they've got a GI record. And so, because if you come out of the services, you've got the right to go to university and get support to go to university because you've just come out of the services. So we want to combine all of this data together, do analytics, and let the poor person at home actually work out, make some data to know before they go to university. So this is kind of being piloted currently in the US. And so the legislation's gone through. The idea is to build a system which does this, which preserves privacy. Okay, a few more minutes. Okay, so the final application is the thing that the company we founded a few years ago is doing. And so this is securing cryptographic keys. So we use cryptographic keys for all sorts of things. And in general, if you're in a bank or if you're in a big organization, these are stored in what's called a hardware security module. Now, a hardware security module looks like this. It's a box. They're all made by the same company now because there's a global monopoly on them. They don't look like that anymore. Anyway, so they kind of look like this a bit, but some of them are very old, and they're all made by Thales these days. IBM might make a few, okay. And the joke is that no one likes them. They're neither hard nor secure nor modular, despite being called hardware security modules. But anyway, so this is where they're normally stored, but they're a bit cumbersome, and they're good for financial applications, but you might not want to use them for all applications. So one idea we had is actually to, there's various problems with HSMs, but one idea we had was you take the cryptographic key and you split the key up. So instead of having a multi-party computation where you bring many parties together, what you do is you take one party and you split them into many parties in a sort of dark side of the moon style logo. Okay. Again, academics really bad at coming up with company names. So it's now called Unbound. It was originally called Dyadic. The first name we had was Prism, because we thought that would be cool. You could have dark side of the moon logos. It would be, we'd look so cool. And then that was a bullet we narrowly missed, because about a month after we decided not to go with the name PRISM. Snowden's revelations came out that there was this major spying program of the US called PRISM, and that would have been a bit embarrassing to have a company named after a major US spying program. Anyway, so here what we do is we split the key up, and we then use it to do cryptographic operations with never bringing the key back together. So it's kind of like the opposite of MPC. It's not like bringing people together, it's splitting people up. It's sort of the divorce version of MPC as opposed to the marriage version. Anyway, so there we go. The company's, we're the first MPC solution to get Fitz Approval, which is like a big thing to be used in financial institutions. And that's the logo, which now looks cool, and you can just say it with your best movie voice, Unbound. And then it sounds so much better. Anyway, so there we go. So the last thing is this a cool technology? And the answer is, well, yes, it must be a cool technology because Gartner says it's a cool technology. Okay, so this is Gartner hype cycle. So if you know anything about technology prediction, you know, and if you're in a company, you go, is this a cool technology? You just pay $10,000 to Gartner. They'll give you a report, and then you look at the hype cycle. And so this is the hype cycle report for data security for 2017. Okay, so it's a bit out of date, but this is the only one I could steal. So multi-party computation is here. This is on the innovation trigger. This is on the way up. So if you're a VC, venture capitalist, this is where you want to invest. These are the stuff that's about to go good until it kind of goes, well, peak of inflated expectations. We're not quite there yet. And then it goes, okay, so this is where you want to get out, okay? And if you're here, this is the plateau of productivity, it's called, plateau of productivity. So this is like, don't bother putting any money here because this is old technology no one cares about. Tokenization, fraud detection, database encryption, this is old stuff, yeah? So this is kind of, but you want to be here. This is where all the high-tech action is. So we're here, we're actually mentioned on a Gartner hype cycle report. Now academic crypto is never mentioned on Gartner hype cycle reports. But the only thing that's kind of mentioned now on Gartner hype cycle reports is blockchain, which is, if you haven't heard of blockchain, then well done. Yeah, so we're kind of there. We're not at the hype of blockchain, but we're very pleased. And I was at a US government, I was at a DARPA meeting, which is like you have room the size of this, and then a third of the audience were in from the government saying, how have you spent our money? And then a third were from industry, and then the other third were from academia. Every single academic had a startup in this space. It's just like there is so much VC funding and stuff in the area. It's a really, really big, growing technology because we've got lots of applications we need to solve because we need to secure people's privacy. And with that, I did leave some time for questions, but we're going to do those later. Okay?